let's jump right into this. Imagine a superhero origin story, right? But instead of a person, we're actually tracking a single mathematical function. Today in this explainer, we're looking at one of my absolute favorite concepts in all of math. It's this idea that a function acts exactly like a shapeshifter. It has one true identity, sure, but it can completely transform its appearance depending on the environment we put it in. So let's dive in and uncover the magic of mathematical translation.
So, here's the big question I really want you to keep in mind. Can you imagine one core mathematical rule wearing four completely different disguises? It's true. Literally one function, four different faces. I know, sometimes math can kind of feel like a jumble of completely unrelated formulas and charts. But as you'll see today, a lot of these are just different languages, you know? They're describing the exact same underlying truth. Once you grasp this, it's honestly like getting the ultimate decoder ring for algebra.
Here is our roadmap for today. We've got 1. Meeting the function. 2. Way 1. Ordered pairs. 3. Way 2. Pattern table. 4. Way 3. Arrow diagram. 5. Way 4. Cartesian graph. And finally, 6. A summary of all four forms. Let's get moving.
All right, section 1, meeting the function. Let's establish that base rule.
Okay, so here's our baseline rule, the DNA of our shapeshifter, if you will. The function is f of x equals 2x. Think of this function like a really simple, predictable machine. Whatever number you drop into it, which we of course call x, the machine just multiplies it by 2 and spits out the result. Now take a look at the domain. The domain is simply the allowed inputs, right? It's the playground our function is allowed to play in. And for our specific example today, this machine is strictly only accepting the numbers 1, 2, 3, and 4. That's it. No fractions, no negatives, literally just those four numbers.
Section 2. Way 1. Ordered pairs.
Now that we know our rule is just multiply by 2, and our inputs are 1 through 4, what's really interesting here is how we systematically process that entire domain. If we feed the number 1 into our machine, well, 2 times 1 is 2, which gives us the ordered pair 1, 2. We just follow this exact same rhythm for inputs 2, 3, and 4, pairing every single input directly with its doubled output. The notation works perfectly. Input is always first, then a comma, then the output, all wrapped up in parentheses. It's clean, it's exact, and it perfectly links cause and effect.
So the absolutely crucial point here is that when we group all of those individual calculations together, we get a complete set. Look at how elegant this is. By putting these pairs inside curly brackets, we've successfully translated an abstract formula, that f of x equals 2x, into a concrete, finite collection of items. This is our function's very first outfit. It tells you exactly what goes in and exactly what comes out, item by item.
Moving right along, section 3, way 2, the pattern table.
But, what if we want to look at this data a little differently? What if we're hunting for a rhythm? Let's see how this builds on what we literally just learned. We're taking the exact same ordered pairs, but now we're organizing them horizontally. The top row, x, holds all of our domain inputs, 1, 2, 3, and 4. The bottom row, f of x, holds the matching outputs, 2, 4, 6, and 8. By lining up the inputs and outputs in these really clean columns, our brain immediately stops looking at isolated pairs. Instead, it starts scanning the rows for relationships. It kind of forces us to look at the progression.
And this brilliantly illustrates exactly why we use tables. Look at that bottom row. From 2 to 4 is a jump of +2. From 4 to 6, +2. From 6 to 8, +2 again. It's a steady, perfectly regular climbing pattern. As you can see, using a table is absolutely the easiest and most effective way to spot the hidden rhythm of the math. If you ever feel stuck trying to find a pattern in a math problem, just put the numbers in a table. It acts like a magnifying glass for mathematical rhythms.
All right, section 4. Way 3, the arrow diagram.
So we've seen pairs and we've seen patterns. Now this shifts us from looking at data rows to looking at a conceptual map. Here we have two distinct bubbles, or sets. Over on the left is set A, our starting point, our domain. It's got our familiar friends 1, 2, 3, and 4. On the right is set B, our destination, which we call the codomain, containing 2, 4, 6, and 8. In an arrow diagram, we visually build a bridge. Just imagine drawing an arrow shooting directly from the number 1 in set A straight over to the number 2 in set B. Then an arrow from 2 to 4, 3 to 6, and 4 to 8. It's highly visual. It physically shows the action of the function, transporting a number from one world to another. And the specific numbers that actually get hit by the arrows in set B, We call that group the range.
I really want to highlight a foundational law of this mathematical universe here. This is a function specifically because every member of A has exactly one arrow pointing to B. This is absolutely crucial. For our machine to officially be called a function, it has to be predictable. If you input the number 1, it can only shoot a single arrow at the number 2. It can't shoot an arrow at 2 and then another arrow at 9. One input, exactly one designated target. And honestly, this arrow diagram makes verifying that rule incredibly easy just by glancing at it.
Almost there. Section 5. Wave 4. The Cartesian graph.
Okay, we are ready to step into the fourth and final transformation. We've done text, we've done tables, we've done conceptual maps. Remember those ordered pairs we calculated way back in the first method? 1, 2, 2, 4, 3, 6, and 4, 8? Well, the Cartesian graph turns those pairs into physical locations. The first number tells you how many steps to walk sideways on the x-axis, and the second number tells you how many steps to climb up on the y-axis. By plotting these pairs as individual dots on a grid, we are giving our abstract formula a real, physical shape in two-dimensional space.
And here is the big payoff. When we step back and look at those dots we just plotted, what do we actually see? They perfectly align. If we lay a ruler down, we can connect those dots to create a continuous, upwardly sloping, straight line. Because the shape it forms is a line, we finally exposed our shapeshifter's ultimate classification. It is a linear function. Now, we already knew the pattern was a steady +2 from our table, but graphing it, that brings that steady climb to life visually. It's just a beautiful confirmation of literally everything we've calculated so far. Finally, Section 6. A quick summary of the 4 forms.
What an incredible journey! We took a single simple rule and watched it morph right before our eyes. To summarize, we started with one truth, f of x equals 2x. And we learned how to speak that truth in 4 different mathematical languages. Number 1, ordered pairs, perfect for exact, itemized input-output tracking. Number 2, the table, basically the absolute best tool for spotting hidden patterns and steady rhythms. Number 3, the arrow diagram, an amazing visual map to prove that every single input has exactly one predictable target. And number 4, the Cartesian graph, which turns numbers into geometry, revealing the actual physical shape, in this case a line, of our function. 4 completely different ways of looking at the exact same data.
So, I want to leave you with this provocative thought. Mathematics isn't about rigid memorization, it's really about choosing the right perspective. From these 4 methods, which one will you use to solve your next mathematical mystery? Are you a visual thinker who loves the graph, or maybe a pattern seeker who loves the table? The power is literally in your hands to choose the disguise that works best for you. Thank you so much for joining me on this explainer. Keep exploring, stay curious, and I'll catch you in the next one.